So the other day, I was sitting on my table eating some mangoes like I normally do, when one of the mangoes decided to suddenly phase through the table and fall onto the floor. I realized that this has got to be super rare, so I decided to do some research. Turns out the chances of a mango phasing through a table are astronomically small, but when you look at things that are physically astronomically small, this phenomenon actually happens all of the time. This is all to blame for particles, because particles are performative. At a subatomic level, particles become super performative. When you're not looking at them, they act like waves, but when you're directly observing them, they become particles. This means you can never know where these goofballs are at a single time, and you can only guess. It's quite a difficult thing to do to explain the behavior of performative people, and it's even harder to do so for particles, but I'm gonna try to do so anyways. Let's take light for example. It's proven that when light hits a metal surface, it ejects electrons. Now let's assume for a second that light is always a wave. You would probably assume that electrons would be ejected based on the intensity of the light, right? Because it just makes sense. If you shine a brighter light at the metal, more electrons are ejected. But if you shine a less bright light at the metal, less electrons are ejected. However, this is not actually what happens. If you shine a high intensity light at a metal, even for a very long time, no electrons are ejected whatsoever. This is because in this instance, light acts like a particle. You can think of frequency like the strength of a photon. If you throw a bunch of marshmallows to try to break a wall, it's not going to work, obviously. However, if we launch an RDS-220 Tsar Bomba, you get the point. If we shine light at a certain frequency, electrons will be emitted regardless of intensity. This shows that light is acting like a particle here. But light can also act like a wave. If you pass light through a wall with two slits, it acts like a wave, and it spreads out and shows this thing called an interference pattern. This is caused when two waves either cancel out or add up. Now the weird thing about particles though is that when you pass a single particle through the wall with two slits, eventually the same pattern will still show up. Super wacky.
But how exactly does this have anything to do with a mango passing through a table?
Well, I'm just about to get to that part. There's one way of explaining particles passing through a wall. Unfortunately, that requires gambling. Let's say you're rolling 3 dice to determine the position of a particle. The dice are rolled when we're not observing the particle, so they're in the wave state. But when we directly observe them, they stop rolling and an outcome is determined. We can plot the sum of the dice rolls onto a probability line, and we can use this line to roughly estimate the position of a particle. Now we can repeat this process a couple hundred times and we can find out all the possible combinations of the dice. You can probably now realize that there's a curve that you can draw to determine the position of the particle. In physics, people use a diagram that looks basically the same as this to show us the odds that a particle is in a certain location, like the combination of dice in this diagram. Let's put a very thin wall in the middle of the diagram to see whether the particle can pass through or not. Overall, getting a 10 or 11 is way more likely than getting a 3 or an 18. However, the fact that there's actually a curve shows that there's a non-0% chance that you can actually find the particle to be in the lower end. This means when a particle approaches a barrier and hits it, sometimes small amounts of the particle actually don't reflect off and travel through. But obviously we wouldn't be able to see those, because they're... But the chances of a singular electron going through a barrier is way larger than billions of atoms from a mango going through a table. This is probably disappointing news for some of my viewers, however worry not, because many seasoned gamblers would know that if you have enough of something, rare things are bound to happen. So if you have enough particles, tunneling must happen. And there just so happens to be one stellar mass object that we know very well that just so happens to have a lot of particles in it. The Sun. This ball of burning gas that we all know and love has approximately a radius of 700,000 kilometers according to NASA, or 400,000 miles if you use Burger Eagle language. If we do a little bit of mental math, we can figure out that the volume is around 1.4 times 10 to the 18 kilometers cubed. The Sun is also made of roughly 74% hydrogen and has a mass of around 2 times 10 to the 30 kilograms. When you actually calculate how many hydrogen nuclei that actually is, you end up with around 10 to the 57 hydrogen nuclei. That's around a septillion, trillion particles that can undergo fusion at the same time. With such a large amount of particles, tunneling becomes not that rare actually. The way the Sun shines is because of a process called fusion, where light hydrogen fuse together to form heavier helium nuclei. But there's a slight problem. I have here my friend White Guy who has kindly provided me with 2 enlarged hydrogen nuclei. Now White Guy, try to put them together.
Wow, it's like a magnet.
That's right. Protons are positively charged, and like magnets, like charges repel, meaning it's very difficult to put them together. But once you overcome this repulsion, they stick. This is due to a thing called the strong nuclear force, which is the force that pulls nuclei together. However, this only works once they're close enough together, which means that the nuclei need enough energy to overcome the electrostatic repulsion. The core of the Sun is around 15 million degrees Celsius, so the hydrogen atoms are moving insanely fast under a huge amount of pressure. But then again, some hydrogen nuclei still don't have enough energy to fuse. But fusion still happens. Why? Quantum tunneling. Instead of the particles needing to fully climb over the energy barrier using a lot of heat and pressure, some hydrogen nuclei basically cheat. Since particles behave like probability waves, there's a tiny chance that one of them simply appears on the other side of the barrier and fuses anyways. This small chance is severely beefed up considering the amount of particles that are in the sun. Every second, the sun converts around 600 million tons of hydrogen into helium. About 4 million tons of that mass is converted directly into energy. Einstein's famous formula explains this. Mass can be directly transferred into energy. And that energy produced is basically what gives us sunlight, heat, weather, and literally the ability to exist. So basically, the entirety of life on Earth is carried by some weird math trick. Now, technically, that means it is possible for your mango to tunnel through the table. You'd probably have a better chance of randomly picking out a single atom out of the entire observable universe. Twice. Blindfolded.
Hey yo, Blub, I just picked the same atom out of the entire visible universe. Twice. Blindfolded.
Well, I guess you're just lucky then. But now, where's my mango? Before we end the video, I know every YouTuber says this, but this video took me a very long time to make, so I'd greatly appreciate it if you subscribed. Also, I'm hosting a fan art competition for drawing blobs, and I'm gonna be hosting that on my new Discord server. The link is in the description. Bye bye!